I just wanted to spend a few minutes going over one of the more difficult topics of the chapter here, the Friedel-Crafts reaction, Friedel-Crafts alkylation to be specific. And as you can see here, the rearrangements are what make this particular reaction a little bit more complicated, kind of like last semester when we were going over some of those 1,2 hydride shifts or 1,2 methyl shifts. Either one are going to be possible. So here's an example of a reaction that would undergo a rearrangement. And kind of a tricky one here. Say we had a alkyl chloride here that looked like this, and we were using our catalyst. Here's the aluminum chloride catalyst here that was invented by Friedel-Crafts. Here in the mechanism, it's always wise to go through and see if it will form a carbocation first. So once that reacts, we get the complex here. Oops. Here we see that the chlorine is attached to the secondary position here. And since this chlorine here is more unstable, positively charged chlorine is more unstable than the carbocation, that comes off. And then we get the carbocation. Shifts are possible even if we don't form a carbocation on a primary position, especially if it can shift over to a secondary. But here we have a secondary carbocation form. Here's the tricky part. That's a secondary right by a secondary. But this position right here is an allylic position that's resonance stabilized with the double bond right there. So since that's resonance stabilized, it's more stable than just a tertiary. So what you see is this will move over here. And this is the 1,2 hydride shift that we learned about last semester. So that would form this carbocation. Here there was already one hydrogen. Now there's 2 hydrogens right there, and only 1 hydrogen left over on that carbon there. Again, this is not just a secondary carbocation over here, though. It's resonance stabilized with this pi bond over here. This is very similar to chapter 16 stuff right here. So the carbocation is actually the composite between a secondary and the tertiary carbocation. Now when benzene reacts with this, the benzene will actually react in the least sterically hindered. Same principle that we learned about here. This is just any old nucleophile here, benzene. It's actually a pretty good nucleophile because it's very flat. And it still wants to attack, though, the least sterically hindered side. This carbon only has an ethyl group attached and is flat, whereas over here on this carbon we have a methyl group and another methyl group right beside it. So there's more sterics here right by the carbon of the attack. So it attacks that one, and we get an intermediate that looks like this. Here's a hydrogen. Here is the alkyl group that just attached right there. And this is a resonance stabilized carbocation also, the Wayland intermediate here. Stabilization here occurs at both the ortho positions here and the para position. Tomorrow we'll learn about how electron donating groups here in those positions will help stabilize this and will promote a certain type of reaction. So then aluminum chloride comes along. This is the aluminum that has an extra chlorine on it, so it's negatively charged. It takes that proton, and then that reestablishes the benzene ring. All of the reactions with benzene have that same trend to reestablish the benzene ring. That's why this is a substitution reaction. It substitutes for hydrogen on the benzene. Now this question on the test is not going to stop with just one synthetic step. Be also cautious of other reactions that could come up from the previous semester. So I'll probably throw in something like BH3 and tetrahydrofuran in combination here with a second step of sodium hydroxide and peroxide. That one there, the review is, this one is a hydration. Meaning we're adding H2O. And the H2O gets added across this double bond here. So you'll get H2O on these two carbons right here. This is actually an addition reaction. It's a good example of an addition reaction where the pi bond is broken. But this one, the key is anti-Markovnikov's rule, anti-Marx. And that means, based on looking at these two carbons right here, the OH will end up on the least substituted side. That one right there only has one alkyl group versus two alkyl groups. And another way of looking at it is the least hindered side also. Least substituted or the least hindered. So after this multi-step sequence here, you would end up with this product. Ooh, this is getting ugly. That would be the final product there.